Yes. If you're doing matrices, if I were you, I would make the second row the first row, and I would switch their order.
How do you do this?
You're allowed to switch their order to do whatever order you want. I'd rather have a 1 than a 3. You can put whatever you want in whatever order when you start.
Do that.
Then you should put the third one in the second.
If you want. It's all about to change in a second anyway.
That's all I asked.
Worst comes to worst, Nathaniel, you can always do system of equations and try just taking them 2 at a time. You don't know what else. You could also be doing REF, I suppose. You're just getting ones and zeros below and then back substituting. I don't know. I'm just going all the way. Some of you use, I'm using this whole interchanging rows to get what I want quite a bit. This is like an extreme, huge bonus version. I was definitely good at it. I've never given one this bad. Which way did you use it? Are you done yet? How did this happen? For me, adding R2 to R1, 0 plus 1, 1 minus 1 is 0, negative 10 plus 4, negative 3 plus 2, negative 52 plus 25. So I was getting my zeros. I get my zeros by multiplying by the opposite and adding. See it? So once I get my 1, which I cheated and I got by interchanging rows and multiplying by a negative 1. Then remember we get our zeros by multiplying by the opposite, which was just 1 R2 plus 1. I didn't do R2. All the way. Making sure that's 0. It's nice if it's 0. Has anybody gotten to plug in their calculator in RREF?
I'm right there.
It's matching up?
Well,
Have you been checking my stuff? Okay. I think I have it, because that's 5 and carry to 3, and that's 15, and that's 185, and 185 plus 10 times 17, 17 over 17 is 170, and then negative 15, and then 37 and 5 is negative 185, which is 0. Okay. For the first time, I have to multiply by this. 17. Yeah. 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 1.
Wes make it?
I'm almost there.
It goes on the way. How did I avoid fractions for so long? Because some of you guys would have gotten fractions in like the very first step or the very second step. How did I avoid fractions? By moving around rows, yeah. Because otherwise, like he asked in the beginning, why did I switch, or could I switch? If I started dividing by 3, I would have had fractions right away. And I saw 1, so I was like, oh, forget that. I'm moving you up to the top. And then once I went through and got my zeros, then I noticed to get my next one, I would have had to divide everything by 5. I'm like, there's a 1 right there. Let's switch and multiply him by a negative all the way through. Remember, these are row operations. That needs to follow the entire row, which is what Nathan was bringing up earlier. If you just have it work for the first couple and then you don't pay attention and you don't change the whole row, you've all of a sudden thrown off the balance. Let's keep everything balanced. Elimination, remember, multiply the whole equation. Same thing with matrices, multiply the whole row by a constant. So I switched saying, forget it, I want the 1. I was like, I have them. And then I got zeros the rest of the way. And then I was like, I want the, I could have divided by 37. I was just lazy and said these numbers are smaller. So I switched those and divided by 17, or multiplied by 117. And so then actually 185 over 17 ended up being a nice number. No, sorry, 85 over 17 ended up being a nice number. And I had one nasty fraction, but it wasn't that big a deal because I didn't really, well, I did. I needed to use him here, but I would think of things like negative 17 over 17, or negative 51 over 17, or 170 over 17. I was doing some like common denominator work up there. It didn't end up that messy, and what was super nice at the end, even though this guy was kind of gross, that was a 0. So when I had to get rid of all these fractions, it was nice because when I was multiplying by 0 and adding, it didn't change anything. So I was able to end up at, wait a minute, where did I end up? I ended up at x, y's, and z's. Smart boy that doesn't like me. I'm coming to you, Nathaniel. A solution that solved with 1x being 3, 1y being negative 2, 1z being 5, and 1w being 0. You could think of it as that's how we solved our first 4-dimensional system, at least at the year. Nathaniel, what's up? Yeah.
So are you just supposed to like do whatever you want until you get the answer?
Kind of, as long as you're following legal row operations. So I was being creative to make it easier on myself.
How do you know so that like
There's a system behind this whole thing. And that's what your calculator is using when it goes straight to the answer. Someone programmed the system in. And the system is that we're working by basically columns, doing row operations, but the row operations preserve the integrity of the earlier columns. See how they kept on like kind of certain things would get fixed and then keep following? If you work by columns, one column at a time, starting on the left, moving your way right, getting an established 1 first from the identity matrix, which is what you want, and then getting the corresponding zeros. You can always, or you can program a computer to always have a 1 by taking whatever's in there and dividing it by itself. Another way of thinking about that is multiplying by its reciprocal. So if there's a 1, divide by 1, it's still a 1. But if there's a 13, divide by 13, sorry, there's a negative 13, divide by negative 13, you will get 1. So you can either have a 1 or always get a 1. And a calculator wouldn't mind having fractions, so it wouldn't even do this weird like interchanging of rows. It's like, who cares? I can get a 1 and hold on to the fractions just fine. So get a 1 and then use that established row to go ahead and get the zeros by taking whatever entry is there. This could be B and C and D, and just say negative B times this guy plus that guy, little baby formula. Chug out all the numbers, plug in, simplify all the numbers all the way across. It's always to get zeros, just multiply by the opposite of what's there to whatever row has the 1, and then add, and you'll always get zeros, and then you'll have all these other values, and you just keep on next column, get the 1, get the zeros, next column, get the 1, get the zeros, next column, get the 1, get the zeros, and then you're always going to be done, if it's possible. We saw yesterday a couple times where the calculator tried to go, and if I had done it by hand, it would have tried to go, and all of a sudden you get 0, 0, 0, 0, 0, and you're like, oh no, okay, did as best it could, and then we have to interpret the answer. Or even worse would be 0, 0, 0, 0, 1, which would be false and impossible, and then I'm like, well, all that work down the drain because it's not possible for this to actually intersect for all for four-dimensional figures, tesseracts, if you guys want to go into Marvel. Because it's not a line anymore, that's one-dimensional. It's not a plane, that's two-dimensional. It's not a cube, that's three-dimensional. Four-dimensional will be a cube mapping to a cube. Go look up the fourth dimension, it's interesting. It looks like the tesseract. But anyway. I can't tell you how to visualize this, but anyway, if it was 0, 0, 0, 0, 1, it would be impossible for the four-dimensional figures to intersect in one place. But as it is, this one is possible. And so the four-dimensional figures, whatever they look like, all intersect in 3, -2, 5, 0, whatever that is. The fourth dimension, a little tricky. Or I should say a lot tricky. Some people think it's time. Go look up string theory if you're really wanting to get your mind totally boggled. And parallel universes and physicists and all kinds of crazy stuff. Did anybody try besides way to solve this with like, hey, let's take the first 2 and get rid of x's, let's take the second 2, get rid of x's, third 2, get rid of x's? Yeah? Did it work? Well, because you're going to get fractions no matter what, right? Like, I don't know. And Nathaniel, like I said, if I was a computer, I wouldn't have done, or even Nathan, I wouldn't have done all this crazy interchanging stuff, just I was lazy. I'd be like, I want a nice one. I don't want to have to work for it, so I'm just going to move it. And be like, yay. So it could have been a whole lot harder if I hadn't been interchanging. But that's the nice thing about humans. We can look at a problem and bring our creativity to it and kind of adjust based on having certain fundamental truths that we make sure that we abide by. And then solve it a different way. Did anybody make it yet? Just trying to like kind of kill time and see if anyone could get it all the way. Anybody else? Anybody still working? Party poopers, y'all gave up. But do you at least see how the system of work by columns, get ones, get zeros will work with whatever size? Now, would it be tedious if it was a 10 by 10? Yes. Would I do it on a smart board? Heck no. I would make so many mistakes. If you guys saw, I was like in my own shadow and trying to move back and forth and double checking. I would get a big old whiteboard and I'd go for it if I had to do a 10 by 10. I heard something about Mr. Che offering extra credit for something last year. Was it a 5 by 5? 4 by 3 by? I don't know. But I don't think it was was it a matrix? I don't know. Honors talked about something about a 4 by 4. Was it equations or was it a matrix? Do you remember? Nice. Well, you want to go track down Mr. Che if you guys actually made it to the end, be like, so that extra credit. Anyway.
Do a 10 by 10. I get an A in the class.
I would love to say yes, but I don't bargain that way. Love to say yes, but I don't bargain that way. You have to think of something that I could give you. I can't give you a grade. You have to earn that way. You have to think of something that it would. Oh no! Don't up the no. That's not going to help. I mean, like, in my integrity, I couldn't just be like, oh yeah, I'll give you an A for doing this one skill for an entire year of Precalc. Like, I can't do that. But you have to think of something that would be comparable, that I could with integrity. I don't know. Think about it, Nathaniel. Think of something good. Maybe I can say yes. Not a 50 by 50. Please don't do that. Maybe a 10 by 10. I would even go for like a 6 by 6. Guys, we do get to go to a much nicer section, a much happier section, a much simpler section, a much easier section. But maybe we should grade just a little bit and see how grade. Never mind, it's not due until Monday, 8.1. But those of you guys that have been working on 8.1, is the whole thing brutal 4x4s? Oh, don't say yes, it's a definite no. Aren't some of them just like filling in the boxes? Ooh, but do you get what filling in the boxes are actually forcing you to know how to do? You have to be able to know the row operations in order to fill in those boxes. Otherwise, how else are you going to do it? So I might, in just a second, jump to some place where someone is stuck. But for right now, I actually want to peek really fast at one of these fill in the boxes ones. And whether or not you guys understand or know what's going on and how on earth they can be asking us to fill in boxes without showing us any formulas. How are we supposed to know what they did? Well, they're doing what I did. They're doing the system. Can you see it? Nathaniel, here you go. Here's the puzzle. They're doing the system. they're doing like what I just did, but with a different matrix. Can you figure out what should go in these boxes if you can figure out what they were doing? What were they getting? They were getting 1. Now hold on, pause. You better double check. Did they interchange anything? Were they being lazy like me? No, they just went for it. Okay, well if they went for it, the only way to make the 2 into the 1 legally with row operations would be 1/2. Row 1. So then, they must have done 2 over 2 to get that 1, so then what would this one be? And then, everyone would be sad because there's a fraction. That's why I would have been lazy and I would have switched those 2. But it's okay, it's not me, it's them. So hold on, what are they doing now from here to here? What has been done? They've gotten their zeros. Now what's the system say for getting zeros? Not multiplying by the reciprocal. Adding, wherever the 1 is, which is something times row 1 plus wherever we're going, which is row 2, and something times row 1 plus where we're going, which is row 3. What did they have to multiply row 1 by to add and get it to go away? -1 for this one, right? -1 plus 1 would be good. And then for that one, -2. Now you just have to say, okay, well, what's negative times 1 plus 1? 0. Oh, I already knew that. What's -2 minus 1? Double check that you're right. What's -4 minus 3? Got it. What's -3 halves plus 4 halves? Get those common denominators. Life is so much easier. 1. How about down here? -2 plus 2. Oh yeah. That's +2 plus 6. Oh, sorry. Where are they building it off of? No, +2 plus 6 would be 8, right? Am I crazy? Oh, we're multiplying. I don't know what I was looking at row 2. Thanks, guys. Looking at row 1. Man, it's just 4 by 4 and I can't even multiply right. -4. My brain's tired. I apologize. -4 plus 6 is 2. Got it. What's -8 plus 4? Yeah. And then what's -6 halves? Oh, just kidding. The 2's canceled. -3 plus 9. Okay, his brain's down. The only way to fill the box is if you understand the operations and if you can see what they were trying to do. Anyway, I like those problems. That's why I assigned at least a couple of them. So it's not that you're supposed to read the person's mind. It's like, no, see what happened. The 2 became a 0. Oh, there's a way to do that. Oh, here we go. The -3 became a 1. Oh, there's a way to do that. Well, this one's easy. The -1 became a +1. They just multiplied everything by the negative. Anyway, like those ones in homework. But besides the Foxy ones, those of you guys that have started homework, is there anything else you want me to peek at real fast and make sure or help you understand or go farther? Kimia. 69, Nikki? Okay, so peeking at 39 and then running to 69. So 39, just the very first jump, right, kid? So they're going from having 3 and -2 to having zeros. Okay, so let me just write the formula, yeah? Isn't the formula saying take where the 1 is, and then multiply that row 1 before adding to row 2? And I'm going to multiply by the opposite. And then for this guy, you can do the same thing. So I'm going to multiply by his opposite. Because I need -3 plus 3 to be 0, and I need +2 minus 2 to be 0. 1, 1, 4, -1. The first row stays exactly the same. It's only the second and third that are changing. And they're getting their zeros. So -3 plus 3, -3 plus 8 is 5, keep multiplying and then adding. Multiplying and then adding. Is that cool? And then, Kimia, number 69. I'll take one last call if somebody else wants something else. Oh! basically Gaussian elimination, which I think is super tedious and annoying because then you have to like go part way with the matrix and then back substitute. So I'd rather do Gauss-Jordan because that's what I just did. And you go all the way. I could do Gaussian. Gaussian, the idea is. Right here. Well, I don't want you to skip it, but I could understand or I could support you guys being like, forget it, I don't want to do Gauss, I want to do the whole identity matrix. Like, I would just go all the way. That's what I'm saying is don't just stop, but you could just stop if you want. Technically, Kenya, what they're asking you to do is to just get the 1 in each column and then the zeros only below 1 and then the 0 only below 1 and then be done. And then take that back to the system and do your little like Z, plug it in, and then Y and Z, plug it in. That's technically what they're asking. Which, to do that, I would go ahead and do 1/4 row 2, right? Yeah. Which would lead me to 0. There's my 1, 1/2, and then 0. I could rewrite that first row. I'm actually not changing him at all anymore because I'm aiming for that back substitution. I can just go back and plug in. So I'm like, fine, I'll be lazy, I guess. Oh, wait. No. We can't go to the next column until we finish the first column, and I never got my 0. So instead, I'm going to be a lazy bum, and I'm going to switch. No, that's not going to help. I'm just going to get rid of it. So I can do R1 plus R3, right? Yeah, don't go for that until you finish this. So then 1 minus 1 is 0, good. 1 plus negative 1, 2 plus 1, negative 3 plus negative 1, negative 28 plus negative 5. Once again, mental mathers, this is great. Non-mental mathers, I know it's brutal, but hang in there. Your sections are coming. And then we have our 0, 4, 2, 0, 1, 2. Once again, though, we're not touching that top row because we don't need any more zeros up there. We do need our 1, so now I would go for my 1/4. To get my 0, 1, 1/2, 0. I'm not going to do the back substitution just because at that point it's like section 7.3. But I will go ahead and get the 0 here, which is the negative 3R2. Remember where your 1 is. So that'd be 0 plus 0, negative 3 plus 3. Negative 3 halves minus 8 halves, so negative 11 halves. And then 0 and 33 is still 33. My second row is now established because remember I don't need any zeros above, so all I have to do is multiply this guy by negative 2 over 11s. And as soon as I multiply him by negative 2 over 11, then all of a sudden times 0 is 0, times 0 is 0, that ends up being 1. Flipping it, that's 3, and negative 2 is negative 6. I have z equals negative 6, which I can bring back to my 1y plus 1/2 z is 0, which I can bring back to my 1x plus 2y minus 3z is equal to negative 28. What they said was Gauss elimination, then stop and be like, ha, z, plug it in, y, plug it in, x. Okay.
When you flip, let's say, you're not very lazy, you flip it.
Oh, yeah, interchange.
Yeah, interchange. Do they keep their titles or do they switch titles as well?
Every time you are doing a row operation in a matrix, you're looking immediately at the one right above. So if I'm doing like the last one, R2 and negative R3, and I'm switching it, this is now R2 and this is now R3 from here on out. Does that make sense? Yeah. So you don't have to like, row 1's identity in the very beginning, row 1 is going to change all throughout. Well, usually, sorry, this one happened to stay the same because it's Gauss instead of Gauss-Jordan. But usually your rows are continually fluid, continually changing because you're always working on it and getting ones and zeros established in different places. But yeah, just look at the one right above or the one right before. Okay, last call. Anything else where someone has gotten stuck in homework and you're like, please help? Perfect. Perfect. I said today we needed to get into section 8.2, and some of you should be so thankful because section 8.2 is a breath of fresh air. It is a sigh of relief. It is a returning to the parts of matrices that you thought you remembered, aka the parts that you liked. Section 8.2. In Algebra 2, what we just did, the row echelon, the row reducing, is probably where he ended. I doubt it's where he began with matrices. Precalc, that's where we started. We just did a whole chapter on systems, and we're like, guess what? Matrices, they do systems too. But 8.2 says, okay, let's return to the basics. For instance, we've already talked about A subscript, the row and the column. All right, here we go. We're into notes, so all of us should be on the same page, aka a new page of our composition books open. All distracting things that are keeping us from doing what we need to be doing. Sign code and light. If the book decided to give you something like this, you should be like, really? It's that easy? Because who is A11? Yeah. It's literally just saying, hey, do you understand the notation? Do you understand that A11 is the guy who's coming very first? In the first row, first column. A12. I mean, look at it, guys. In order for these to be equal, they have to match up. They have to be the same order, and whatever's in this spot has to be in that spot. That's the only way for two matrices to be equal. For numbers, man, it can be crazy. You can have like 4 over 2 is equal to like the cubed root of 8, right? And be like, those are the same. What? I don't get it. But in matrices, not quite as crazy or out there. It's like, for these to be the same, well, he has to be 2, and A12 has to be -1, and A21 has to be -3. And how would you guys finish this off? A22? Yeah, it's just naming them. So we kind of already reviewed how to name the entries with like a little A. Could be a B or a C if it's matrix B or matrix C. Remember the little subscripts. It's not 11, it's not 12, it's not 21 or 22. It's which row, which column. But the only way for two matrices to be equal is if they have the same size with the same number of elements or entries, and they have to match up. So if I give you something crazy, or maybe not so crazy, like the next page. Oh, don't worry, it's going forward. Okay. And I say, solve for what you don't know. How on earth are you supposed to be able to look at that and find x and find y? You would think, except in years past, I forget when I made this originally, and if I changed it since then. But I did a typo. So technically, are these two matrices equal? Why not? That's a 16. That's a 14. Wait, but that's a 4 and that's a 4. Is it possible for this one to change and that one to stay the same? No row operation could actually do that. So technically, what's true right now? No solution. They can't be equal. Some of them are matching up and some of them aren't. Well, that was easy. Okay, let's say we fixed my typo. All right. Let's say we fixed my typo. Now it's possible for them to be equal. Now I can trust and say, okay, fine. Now it's equal. Now can I say 2x plus 1 is equal to 5? Yes. Yeah, there's nothing else it can be. If that's the same and that's the same, that has to be the same. No row operation would change one and not the rest. Oh, there's another one? Yeah. So wait a minute, hold on. If 3x equals 6, what if this one got an x? Well, this one is going to get an x that's equal to 2, right? Yes. What if this wasn't 2? Would I be having some issues? It'd be no solution. Yeah, it'd be impossible. But, lucky for me, maybe not so lucky for me, x is also equal to, okay, good. So I have x is equal to 2. Go team. Where's my y? There it is. So all this is kind of cementing that the only way that two matrices can be equal is if each and every element is equal, or at least an equal ratio with maybe something factored out. But yeah, so my mental math is you already figured out y is equal to. Why am I not writing this as an ordered pair? Like I always write these things as ordered pairs. You see it? It's not like an intersection point. It's not solving a system. It's literally just saying, hey, x is somebody I don't know. There he is. And y is someone else I don't know. There he is. It's good old-fashioned algebra at its core. I didn't know it, so I had to go find it. It's not an ordered pair. I was like, oh, there's x. There's 1. But question. Nathan.
Sorry, you have to ask this, like, you wrote up this over here, and I have to ask this for
Yeah.
everyone. When there is the W, like, when we're doing the four, you put the W in front of X or behind X to the right.
Okay, that's great. We put it at the very end just because
So the over here would be X, Y, Z.
in common math terminology, X is like first dimension, X, Y second, X, Y, Z third. So it's like, oh, we have another dimension, and they just go with W. We could have gone with A, but A, B, C is usually its own. Yeah. But yeah, good question. So matrix addition. When are you allowed to add or subtract, which subtraction is just addition of the opposite, so it's really addition?
When the dimensions
Why is that so important? How do you add matrices? Can you think vectors? Can you think vectors? There were horizontals that went with horizontals, verticals that go with verticals, and maybe there are even three-dimensionals that go with three-dimensionals if we were to do chapter 11. How do we do matrices? Well, A11 with B11. A12 with B12. A13 with B13. Now, this one's kind of basic because what's going to happen if I add 0 to everybody? Stays the same. That's boring. But, I mean, if there were other values in there, it would change. Long story short, is it legal to add if they're the same size? Yeah. What's the issue? Yeah, if you tried to pair up 2 plus 1 plus okay. So we go ahead and we say no solution. Now, some of you are like, well, couldn't you just make a new matrix? I understand that when we have a system of equations and we're allowed to put it into a matrix to solve. But in this case, they're saying, no, matrix A plus matrix B. We can't say that matrix B is anyone other than he is. We kind of added rows, added columns to our benefit when we were dealing with systems. But if they give us matrices, we're not supposed to just like randomly change it. Not a good idea. So we say no solution because it doesn't match up. So addition, similarly subtraction. So let me go ahead and get you a couple matrices and tell you to go play with them. Here's my A. Should have known better. Here's my A, here's my B. And what do I want you to do? A, I want you to add them, if you can see it. B, I want you to subtract them. C, I want you to do 3A minus 2B. Hey, doesn't that sound a lot like U plus B, U minus B, and 3U minus 2B? Matrices and vectors, I think they're science. I want you to think about, as you're doing this, is A plus B, B plus A? Is A minus B negative B plus A? Okay. Oh, 3A. Sorry, I missed that one. Is 3A A times 3? I'm asking about the commutative property of matrix operations. Is addition commutative in matrices? Subtraction commutative? All of a sudden, we're dealing with matrices, which aren't just single numeric values. So that's the kind of question in my head. I have to make sure that the same properties I'm used to numbers having, matrices have as well. Because vectors, I mean, kind of. But then, wait a minute, dot product. That is not normal. What size is A plus B? 2 by 2, because it's going to stay the same size. Just 1 plus 2 becomes 3. Negative 1 minus 1 becomes negative 2. 2 minus 1 becomes 1. And negative 1 plus 8 becomes 7. The values change, but the size stays the same. What happens when you subtract? What size is it going to be? 2 by 2. Just this time I'm doing 1 minus or 1 plus a negative. So you could think of multiplying everything by a negative. And then adding. Remember, subtraction, just adding the opposite. So 1 minus 2, negative 1 plus 1. That's a 0. 2 plus 1? It should be neater. And negative 1 minus 8. Would both of these have been the exact same if I had switched the order and done B plus A or negative B plus A? Because I'm literally just saying 1 plus 2 is 2 plus 1. Oh, that's okay. no stress. It's just dealing with each entry, the two numbers there. So it's really the same thing as normal commutative property of addition with normal numbers. Because A11 plus B11 will be B11 plus A11. Anyway, commutative, as long as you keep the negative with the B. Let me get rid of that just in case some people are trying to still work on some of the earlier ones. What happens when there's multiplication? Like 3A? Yeah, just think distribution. Ends up tripling the whole shebang, kind of like it did with matrices as well. Oops, tripling the whole shebang. Sorry. 3 times 1, 3 times negative 1, 3 times 2, 3 times negative 1. And then letter D, I mean, if we had time, we could keep going with that. However, if you guys remember, addition, subtraction, even multiplying by what we call a scalar. Hey, that's like vectors. Yeah, scalars and vectors. It wasn't a big deal. And the crazy thing is not only can we multiply scalars like 3n, we can also pull yucky scalars that we don't like out, like a 1/2, and have a much nicer matrix left behind. We can bring in scalars, we can bring out scalars. And we'll talk about this a little bit more on Monday. But what gets crazy with matrices? Some things stay the same, and some things are a whole lot different. You guys remember something about going across and going down and having to match up? We're going to think dot products on Monday. Dot products, yep. First plus second. See you guys later. If you want to help you for Monday, if you want to review matrix multiplication over the weekend, you've seen it before. It might help class go easier on Monday.
Alyssa.
Okay, one is
One day.